In this Zoom presentation, I'm very pleased to present a discussion of our ultra-high density cluster enabled LENR studies. I was in China 2 years ago at the pre-workshop meeting there and enjoyed that trip very much. I wish this meeting were in person. I'd like to get back. Thanks. The abstract is contained in the meeting abstract booklet. You will note that some references for the work described here are given there. In this talk, I will first present some of the background leading to ultra-high density clusters. Then I will talk about some of the work that we have done using pulsed pressure nanoparticle low temperature runs to demonstrate excess heat. Then I will talk about different nanoparticle manufacturing techniques relative to excess heat formation. I'll talk about the reaction product studies and more recent high temperature calorimetric studies. Our cluster research was inspired by our original swimming electron layer theory. We initially did electrolytic cell experiments where we formed electrodes based on palladium with oxidized surfaces. The electrodes were loaded and deloaded with deuterium a half dozen or more times, each time creating additional defects which could form the cluster. This is illustrated schematically in drawing. Circled, you see the clusters, which don't show up well here, but could be 100 or 1,000 atoms of deuterium. We have done considerable study to illustrate the formation of these clusters. For example, in temperature program desorption experiments, we found that the peak in desorption of deuterium occurs around 450 or 500 degrees, which is close to the binding energy between hydrogen and dislocations, which is about 0.6 eV. In addition, we did magnetic moment studies showing that below 70 degrees K, this substance could be essentially superconducting. Additional very convincing experiments were done at Los Alamos using their high-intensity pulse laser to drive deuterium out of clusters that had been transported from Illinois to Los Alamos in thin films, and we could make quantitative measurements of the amount of deuterium in the cluster in that fashion. In summary, our view of these clusters is that they are formed in defects that are often created along a interface between different crystalline structures. For example, in the thin film case, between the oxidized and unoxidized palladium. These clusters are highly condensed hydrogen or deuterium, and as I say, are formed in these void spaces. They represent the nuclear active site for LENR reactions. In fact, what happens is that they are so dense that multi-body reactions can occur, creating a variety of products, and this is essential for explanation of results from our various experiments. In previous ICCF meetings, we've talked about some of our excess heat studies from clusters. Here I'd like to summarize that work and then talk about some of the new work that we're doing. Previously we have done these studies at low temperatures. We've used various materials. One is what we call a legacy particle, which is an alloy of palladium zirconia hydride oxide prepared in a high temperature furnace, which was then milled at room temperature. What we call NW particles, new particles, were formed with an arc melting, and then they were milled in a cryogenic mill. That is thought to provide a higher dislocation loop density, and the results tend to show that's true. We've also prepared some high purity palladium, which, since it does not have interface layers to form the clusters, should not work as well as the NW material. As shown here, the palladium zirconia oxide particles have a average particle diameter of something like 1.5 micrometers. For comparison, here are photographs of the cryo-milled palladium zirconia particles unoxidized, and on the right are the oxidized ones. The calorimeter used for these measurements consisted of a small 50 cc either stainless steel or copper cylinder that's located in the larger vessel. The particles are placed in this small cylinder. The larger vessel has the capability to be pressurized from a pressure cylinder, and it's also equipped with vacuum pumps to quickly draw vacuum. Appropriate thermocouples and pressure sensors are incorporated. A typical temperature profile from this type of measurement is shown here. During the pressurization, the temperature rapidly increases due to absorption, and then when the vacuum is applied, there's a quick temperature decrease accompanied by a slow rise back to equilibrium. The net energy shown in this schematic is defined as that energy which can be used to drive an external system. It is attributed to the LENR energy produced by LENR reactions. It can be obtained from the data in these experiments by taking the energy from the desorption curve and subtracting that from the energy during the absorption period. The data shown in the following histograms includes most of the runs during this series. About 10% are not shown because of equipment problems. Here we have plotted the number of runs versus the net energy in joules released during those runs. Mind you, these runs were done under varying conditions, so there's considerable variation, but it's clear that as expected, the palladium and legacy particle runs had very low net energy output. However, the NW particles, which were especially prepared to have increased clusters, did produce considerable energy out, ranging up to 2,000 joules. On the right-hand side, for perspective, we plot the number of runs that have a ratio of excess energy to exothermic energy as a percentage. And as seen here, while many of the NW runs were around 40 or so percent, several produced well above 60%. Here the results are shown in terms of joules per gram of palladium. You can see that the NW particles produced a number of runs in the 40 to 50 joules per gram, but ranged all the way up to around 125. Here we search for trends as a function of the mass of particles and the pressure applied. As you see, as expected, the net energy out is about linear with the mass of particles in the vessel, whereas the energy out tends to increase with pressure up to about 50 psi, but above that tends to level out. In the previous runs shown in histograms, a number of parameters were varied to study possible optimization. So we did do some repeated runs under the same conditions in order to study the reproducibility of the results, and also to see if the particles could remain stable despite undergoing a number of pressurizations, depressurizations. As seen here, the reproducibility run showed that the net energy remained fairly constant despite the repeated runs. In summary, the calorimetry used, while relatively simple, had reasonably good accuracy, and over 100 plus runs using this type of pressurization, depressurization. The cryomilled NW particles consistently showed good values of excess heat. We are currently under taking a series of reaction product studies, and we think the results are encouraging, but it's too early to present the results. We're now extending the Gen 2 low temperature studies to much higher temperatures, ranging up to about 900 degrees. The photograph here is looking down inside a vessel designed to hold nanoparticles, but with much added insulation, plus high temperature seals and added high temperature thermocouple leads. One of the early runs with this new device is illustrated here. As seen in the figure, the temperatures started around 650, and during the pressurization jumped up to above 720, and then began dropping down. In these runs, the jump in temperature represents a quote trigger for the LENR reactions. As seen here, the initial data suggests that some low levels of excess heat, LENR power, are being observed. However, we would like to increase the excess to much higher values, and to do this are looking at possible new, more drastic trigger methods. Our main focus now is on the high temperature runs and new triggering methods. More can be seen about this in the poster presented by Ben Peecher. I do not have time in this presentation to go into detail, but we are investigating reaction products from these nanoparticle experiments, and hope to present the outcome from those studies in the near future. Eric Ziem is doing his PhD thesis at the University of Illinois, focusing on reaction products. Much of his work is using CR39 particle tracking techniques. He's been doing this for the clusters formed in nanoparticles as described in the present presentation. But bulk of his work has also focused on clusters formed by plasma bombardment of electrodes, and this is also producing very significant results. I'm open for questions.